Assalamu alaikum. My name is Hira Zamir. I'm from University of Management Technology, Chemistry Department, and I'm going to present the reactors under the supervision of Dr. Hammad Majeed. Today I'm going to talk about the specific reactor which is microreactors. What are the microreactors? Microreactors are the micro-scale reactors or microfluid reactors that perform chemical reactions on a very small scale. High yield and the selectivity of a product is the advantage of the rapid mixing, heat transfer, precise residence time control. They are effective at increasing the production capacity and open up the possibility of direct transfer of any chemicals from the laboratory scale to the production scale, which is one of the very large scale processes which is used by the very micro reactors. The main advantage of microreactors are the good mixing characteristics, hold up volume is very less, better control as compared to the other reactors. Microreactors has recently been used in the laboratory for studying underlying reactions, develop kinetic models, etc. The structure of microreactor is it contains the monolith in the center, then it surrounded by the reactor controls, which is surrounded by the heat pipe. After that, there is an emergency shutdown. In case of in case of any emergency situations goes out of the control, emergency shutdown is present. Passive decay heat removal, which consuming the which makes the heat transfer very easy. Control from driver. Key features. Key features of microreactor. First one is chip type microreactors. It is most often used because they are easily controlled in the integration of multiple processes into a single vector system. Microreactor can be produced from different materials such as glass, quartz, silicon, metals and polymers. The selection of the optimal material depends upon its chemical compatibility with the reaction mixture so that the chemical we use for the formation of the vessel cannot react with our reactants. The most important features are cost and analytical method which is used into the monitoring and control processes. Glass is the most commonly used material since it is chemically inert, doesn't take part reaction with the reactant, and transparent, allowing its user visual observation of microchemicals. Surface roughness. Surface roughness of the channel wall is one of the most important factor because a reduction in the channel dimensions increases the impact of roughness on the reaction. The average channel roughness is usually between 0.8 to 2.5 micrometer depending on the selected microchannel manufacturing processes. The other feature is tubular microchannel, which is present in the microreactors, a simple straight or curved tube onto the microchip in order to enhance mixing and separation. Different structures can be used as a part of the microchannel or the micromixers. By simple manipulation of inlet design, it is possible to obtain different flow patterns in a microchannel. That is basically microreactor system in which they are showing the different microchannels which is present and each size and shape of the microchannel is significant for better mixing heat control. Characteristic properties of microreactors. Basically, the microreactors are best with their fast mixing and mass transfer. Any reduction in microchannel dimensions reduces diffusion limitation of the enzyme and substrate, and mixing takes place by the molecular diffusion. Therefore, a concentration gradient can be avoided. This is especially important for the reaction system in which active site of the enzyme and the substrate are very distant. It is basically a relationship between an enzyme and substrate. High surface to the volume ratio. Specific surface of the microchannels are significantly higher than those of the traditional macroreactor systems, which as a consequence has a great effect on mass, momentum, and energy transfer in the system. Due to the high surface to the volume ratio, heat transfer is very efficient, making it possible to regulate reaction temperature in a system by very effective heat removal. The laminar flow also provides high surface to the volume ratio, which is specifically very important for the multiphase system. Whereas the laminar flow results into the diffusion controlled reaction of the compound. The microreactors are very environmental friendly as there is a small inlet of the substrate. There has to be a small outlet of the product and byproducts. And if combined with a high productivity and conversion rate in microreactions, this system generates a reduction into the waste streams, low waste materials, which make it more environmental friendly, and total amount of the waste is also environmental friendly. Additionally, due to the high surface to the volume ratio, heat transfer is very good and leading to the extremely small energy consumption, resulting into the environmental benefits. If here we compare about the conventional nuclear reactors and nuclear microreactors, output generally around 1000 megawatt and output is 50 megawatt, but it consumes a very small amount of the energy and produces a very small amount of the waste. This picture is going to tell you about the conventional nuclear reactors that uses which is used into the high scale and produces a large amount of the energy, but as compared to that microreactor uses a small amount of the energy. Safe reaction conditions. Microreactors are considered safer than the other traditional reactors because the reaction performed under the extreme conditions like high pressure, explosives, or reactive high temperature. These things are very performed in a controlled way. So it is a safe reaction condition. Selectivity. One of the major benefit of using the microreactor is reaction performed in microreactors generally results into the purer product in shorter residence time than the equivalent reaction performed into the other reactor systems. This is because in reaction in which the multiple product can be generated from a given set of the reagent, depending upon the local reaction condition, the reaction can be shifted into the desirable reactions. Microreactor provide us the highest selectivity of the product, so it make it cost efficient, rapid reaction. Microreactors are faster and generate higher space-time yield productivities. They are more easily optimized and closely monitored to avoid running from any longer than is necessary to reach the reaction endpoint. Thus, even if the rate of the rate limited reaction is unchanged, microfluidic reactors or the microreactors will allow more efficient and consequently more rapid processes. On the contrary, the rate of mass limited reactions will be increased for a small characteristics dimensions due to the significant diffusive effect that has built into the domain. Now we talk about The application of microreactors, where these microreactors are used, it is used in various fields. First one in our lab, which is testing, catalyst testing, fabricated chemical reactors for highly sensitive measurement of catalytic activity and surface kinetics is presented. The reactor is fabricated in silicon chip and is intended for gas phase reactions at pressure ranging from zero point 0.1 to 5 bars. A high sensitivity is obtained by directing the entire gas flow through the catalyst bed to a mass spectrometer, thus ensuring that nearly all the reaction products are present into the analyzed gas flow. Process development. Microreactors technology is an efficient tool for the kg scale synthesis in continuous mode and is partially effective for the hazardous reactions that do not allow scale up in conventional reactors. It helps in several classes of reaction, including high low exothermic reaction, high temperature reaction, or the reaction with the unstable intermediates. In this, as you can see, sample and the reactant gas is fed into the microreactor, and heating method are different. We can use furnace heating, element heating, particle bed heating, or other non-resistively heating. And reactive type can be a fluidized bag, fixed bed, or the cell reactor, but it is a microreactor. And we decide the direction of the reactor, and then we can obtain the gas solid reaction characteristics. Biotransformation processes. Biotransformation was performed in four different tubular microreactors. Different internal volume of the microreactors with or without the presence of the micromixers, as well as the two different surface type. Rough channels with the relative channel roughness around 10-100% and a smooth one with the roughness around 1%. 30% convection rate is achieved. Here we take the substrate 1, substrate 2 and pump into the sample loop. And after that they are sent into the active mixing, which is connected with the coil. After our substrate, two substrate are present into the active mixing, then it is sent into the immobilized biocatalyst. It is passed through the catalyst and then it is sent for the inline analysis. After that inline analysis, we separate out our waste and send the product into the back pressure regulator, and then finally we can achieve our product. The example of is this biocatalyst, that is we are using in our lab for the testing, and then we use the biocatalyst reactant with other substrate, send into the pump, active mixing, which is a microfluid reactors, and after that the reaction takes place into the microfluid reactor. It is sent into the inline analysis computer, and biocatalyst is then separate out, and we know the product references. Thank you so much.